and welcome. My name is Rola Deeb. I'm a senior principal at Geosyntec Consultants in Oakland, California, and the coordinator of the SERDP and ESTCP webinar series. I have the pleasure of facilitating today's event. This webinar focuses on DoD-funded research efforts to develop and demonstrate technologies for PFAS destruction in concentrated liquid waste streams. First, Dr. Megan Hart from the University of Missouri, Kansas City, will talk about the validation of a novel photocatalytic media to destroy PFAS in concentrated liquids. Second, Dr. Brian Pinkert from Aquaga will present case studies showing PFAS destruction via hydrothermal alkaline treatment or HALT. Each presentation will be followed by a brief Q&A session. The next two slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can still view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you continue to have difficulties or if your screen freezes, just try keying in Control and F5 to perform a hard refresh of your screen. If you continue to have technical difficulties, you can download a PDF of the slides from the webinar webpage. They're already posted, and call into the conference line provided to you in your webinar registration confirmation email. We'll go ahead and drop a link to the PDF of the slides so you can download them if you wish. Another option for viewing today's proceedings is to go to the SERDP and ESTCP YouTube channel, as we will be streaming live at the link shown here. Today's broadcast is listen only. You may submit questions by using the Q&A box on your screen. Please don't wait till the Q&A period to submit your questions. We do encourage you to get them in well in advance of the Q&A sessions. We also ask that when you submit your questions, to please add your organization name at the end of the question so that we can identify you during the Q&A sessions. Keep in mind that the chat box should be reserved for comments related to technical difficulties, so only submit your questions in the Q&A box. With that, it is my pleasure to introduce Dr. Hunter Anderson, who recently joined SERDP and ESTCP as a subject matter expert in the environmental restoration program area. And before that, Hunter provided technical support for the Air Force Civil Engineer Center since 2010 in the areas of emerging contaminants, environmental engineering, environmental toxicology, and quantitative data analysis. Hunter received his doctoral degree in environmental chemistry from the Ohio State University. Hunter, please proceed.
Well, thanks, Rilla, and welcome everybody to today's webinar. So before we conduct these webinars, we like to just give a really brief, succinct overview of the program, particularly for those of you that have never experienced one of these webinars or don't have any experience with the program office. SERDP and ESTCP are both RTD&E programs that reside in the Office of Secretary of Defense. We're embedded under the Assistant Secretary of Defense for Energy Resilience and Optimization. SERDP specifically was established by Congress in the early 90s and is a collaboration between the Department of Defense, the Department of Energy, and the EPA. SERDP really focuses on basic research, sort of fundamental proof of concept, lab scale sort of research that's mostly done, at academic institutions. Whereas ESTCP, the Environmental Security Technology Certification Program, is more of an applied research program where we try to, take these fundamental proof of concept technologies and engineer them into some sort of field applied capability for, actual application and capability on installations to, alleviate these environmental liabilities. And ESTCP is primarily, funds practitioners and industry type folks that do the actual field work. I'm not moving the slides here. Uh-oh. Sorry, Rilla.
We can go ahead and advance the slides for you.
Yeah, okay. Well, so SERDP and ESTCP in general consists of a broad array of topic areas. If you'll go to slide 11, basically this has evolved over the years, but, SERDP and ESTCP's mission statement is to address the environmental liabilities of the Defense Department. And so as those environmental challenges change, identified on slide 11, the next slide there, you can see we've currently got a pretty broad array of topic areas or what we call focus areas, that we try to, equitably distribute among these webinar series. So today, of course, the topic is PFAS destruction and AFFF, but future webinar series will consist of these other topic areas as well. And again, these focus areas change over time as the environmental requirements of the DoD evolve over time as well. If you go to slide 12, we sort of, tout ourselves on the fact that, we provide impact, to the department and the industry in general at any given time between SERDP and ESTCP across all of these different focus areas. It's not uncommon for us to have anywhere, over 600 active projects. And so, there's a lot of competition out there, and, we try to, fund the best of the best and the most innovative ideas and technologies and talent. If you go to slide 13, we also, do a lot of outreach. Tech transfer is something we really focus on to include, the congressional inquiries. So in addition to sort of, moving the needle and advancing the state of science and all the fundamental stuff, we really spend a lot of time trying to translate all of this knowledge into policy. So, we work with the policy folks within DoD and to some extent Congress to try and inform, the policies and even the regulations in terms of how the department, responds to these environmental challenges. And you can see in that first bullet, the diversity of our portfolio in terms of the academia and federal entities and industry. Slide 14. For all of our PFAS webinars, we highlight this illustration. This is an interactive figure that's available on the website. This sort of summarizes all the PFAS specific investments SERDP and ESTCP has made over the years. All the boxes on top of the number line represent statements of need, annual statements of need for a given topic, and they're color coded there. And you can see sort of, how they've evolved over time. But within each of those statements of need, we'll fund anywhere from 5 to, in some cases, 15 projects. And so the portfolio is pretty diverse over the years in terms of topics and the magnitude of investment. And then the boxes on the bottom of the number line represent the projects we funded under ESTCP that, represent the field scale demonstrations of the technologies and concepts that have matured out of SERDP there. So if you go to slide 15, this is just an overview of the webinar series, the upcoming webinar series. And again, today's focused on PFAS destruction. We have a cross section of SERDP and ESTCP, so you'll get a sense of the fundamental aspect of the more theoretical stuff we fund, and then how that translates into sort of field capability under ESTCP. But the next webinar series in September, later this month, is focused on ecology, and you can see the list of upcoming events there. More information can be found on the website listed here, to include recordings of past webinars. So everything's chronicled there for your viewing pleasure at your leisure. And then finally, I just want to, before I hand it back over to Rula, give a quick plug to our annual symposium. This is, our sort of keystone event every year. It's at the end of the year, in this case, first week of December. This is our week-long event where we really showcase all the latest and greatest research that's come out of both SERDP and ESTCP across all of these different focus areas. And so we highly encourage folks that are interested in this sort of thing to attend. It's in DC. It's a pretty action-packed event with lots of information, and so we encourage people to participate in that event. And so with that, I'll hand it back over to you, Rula, for today's webinar. Thanks.
Great. Thank you so much, Hunter. Our first presentation today was prepared by Dr. Megan Hart, who is an associate professor at the University of Missouri, Kansas City. Megan specializes in developing technologies for the treatment and control of HAZ substances in the environment. With multiple patent pending technologies, service to ITRC, and subject matter expertise to both public and governmental agencies, Megan's PFAS experience extends beyond treatment into controlling and mitigating PFAS migration from impacted matrices to the environment. She is a registered geologist in the state of Missouri, has authored many papers in the areas of contaminant remediation and actually other areas, and partners with industry to tackle complex contamination concerns. She received a bachelor's degree in geological and earth sciences and geosciences from Western Washington University, and a doctoral degree in geological geophysical engineering from the University of Missouri, Rolla. Megan, unfortunately, got diagnosed with COVID early this morning and is losing her voice. So her ex-PhD student, Dr. Hannah McIntyre, has kindly agreed to kick off the first part of the presentation to try and save Megan's voice a little bit for the conclusions and the Q&A. So I'm going to go ahead and turn the presentation over to Dr. Hannah McIntyre, who is a senior staff professional in Geosyntax Kansas City office. Hannah, please get us started.
I'm not seeing. Perfect. Okay, thank you. So to go over the what we're going to present in this presentation today is going to be the ultraviolet silica-based granular media, which is denoted as UV-SGM, and this is a photocatalytic technology developed to degrade PFAS in concentrated matrices. We're not going to go over necessarily the development of this technology, but the state of this technology and the validation of this technology. And then the current efforts under SERDP that were done, along with future ESTCP projects and the benefits to the DoD. Slide 20. So UV-SGM is a treatment process that is works well within a treatment train. It was developed to degrade PFAS in concentrated matrices. So this is usually paired with some kind of sequestration technology. So if you have a sequestration technology, predominantly looking at either liquid technologies, such as ion exchange resin that has a still bottoms brine, or solid technologies that develop some kind of secondary liquid matrices like soil washing solution. You would have those liquids that are concentrated, and it would then go to a destructive technology such as UV-SGM. And where UV-SGM falls under in these processes is so liquid treatment, destructive, it's non-thermal, and it's a photocatalytic non-thermal treatment technology. Slide 21. So The validation of UVSGM was funded under SERDP Project ER 19-1403, and the overarching goals of this project were to validate the defluorination of PFAS in a variety of different matrices, specifically concentrated liquid matrices, and develop and determine multiple lines of evidence for this destruction, such as inorganic fluoride or other byproducts of defluorination. And so this was primarily done in reagent solutions, first done with PFAS spiked deionized water with surrogate PFAS, starting with very simple matrices such as just a PFOS or PFOA spiked solution, and then moving into more complex matrices, mixtures of PFAS solutions, with different environmentally relevant constituents like salts and metals and such things, and then moving on to environmentally relevant waste streams such as still bottoms. And this was done primarily starting with a synthetic still bottoms first that was received from a vendor, and then moving on to a on-site still bottoms. Slide 22. So UVSGM, it is a silica-based media. What this is a granular media that is developed through a sol gel processes. So you take tetraethyl orthosilicate and titanium dioxide and silica dioxide, and you mix it together in a sol gel processes. You replace the solvent in the sol gel with some kind of foaming agent. In this case, it's predominantly sodium hydroxide, and that is foamed to create a granular media. That granular media is then packed in a reactor, so you don't have to filter out the photocatalyst, and then it's run as a packed column reactor with that UV lamp. So that's what you're seeing there on the right. That's the granular media itself, and then you're seeing some of the bench scale reactors. And then now titanium dioxide is what was used for most of these experiments. However, you can use other photocatalysts. UMKC is currently doing some work with, I believe, boron nitride and some other things. So there's other methods of introducing other photocatalysts with different band gaps and to target different PFAS or other constituents. So then some follow-on work that they were doing is they're assessing the individual water quality parameters and how that affects PFAS treatment. This predominantly came out of some work with these environmentally relevant solutions. So you have high salts in still bottoms or nitrates from different organic matters that other organic matters that can come up. So they took these individual water quality parameters and assess how they, on an individual basis, affected the treatment, and then also looked at degrading PFAS from on-site regenerable ion exchange still bottoms. Next slide. So going a little bit into the reactor configurations that are done at the lab and bench scale at UMKC, these are the different variations that have been used throughout this SERDP project. Starting very simply in your top left corner with reactor A, just batch scales, stagnant. Reactors, they're just a layer of the media on the bottom with the lamp. And then moving into more flow reactors, something that could be more scalable, more applicable for a on-site demonstration. They started doing flow through reactors, and then scaling those up all the way until you get to reactor D, which is a recirculation reactor. So you have a column reactor, a packed column that has a gallon per minute pump on it. And then you can configure this a few different ways to target certain contaminants or certain PFAS. You can have a column packed with the SGM. You can have a column that's mainly looking at photolysis. You could have these columns in series with different photocatalysts packed in different ones to target specific PFAS constituents over others. So it's a reactor design that's configurable and designed to be able to be easily scaled to put in the field. Slide 24. Okay, going a little bit into some of the results in these lab scale experiments. So this would be the modified recirculation reactor, which is going to be the one you saw on the right on the previous slide, and that's going to be a column packed with this SGM media, and then a column that's just photolysis. And what you're seeing here is the removal of PFAS over time on your left. And what you can see is that the carboxylic acids are mainly being removed by photolysis, so they're being removed at a very similar rate. And then the sulfonates are what is the focus of the SGM in this experiment. So you can see that PFOS, which is a longer chained sulfonate, is being degraded faster as you get absorption and subsequent degradation once the PFAS are absorbed to that photocatalyst. So then the shorter chained compounds absorb less readily to the media and then degrade at a slower rate. And then on the right, what you're seeing is that total PFAS, the parent compounds that you're seeing on the left, represented by that black line. And then you're seeing aqueous fluoride, which is the defluorination, and then total PFAS byproducts. And those byproducts are going to be any shorter chain PFAS, predominantly carboxylic acids, that are not a parent compound. Next, slide 25. So after doing some of the initial experiments with complex PFAS solutions that are just spiked PFAS in deionized water, we moved on to doing some experiments that are more environmentally relevant. So what we have here is some still bottoms from a Navy facility. And these still bottoms were, so it's ion exchange resin, and that resin is regenerated. And then that ion exchange regenerate, which is regenerated with predominantly an alcohol and a salt solution. So then you get, you have the regenerate, and then they distill it, and that's how you get still bottoms. And these still bottoms are very brine-esque, where very high salt, very high PFAS, as you can see there. What we have is pretty close to, so there's some different results here, but averaging somewhere around 800 ppm or milligrams per liter of total PFAS, and this is just of target PFAS. So not looking at necessarily other PFA precursors or other non-target analyses. So very high concentrated solution, and then it has a lot of other constituents in it, like chloride, sulfate, nitrate is very high in this specific still bottom, and some metals, and then very high TOCO, of course. Slide 26. So going into a little bit of the results from those still bottom experiments, what you have here is these still bottoms are diluted 10x, so that the dissolved organic matter, you can see there that solution is very, very, very dark. So you have a hard time getting UV light through such a dark solution. So what happened here is it was diluted 10x to get a little bit of light through the solution and begin that reaction. And it was done at a few different concentrations of basically amending the solution with some sodium hydroxide. So we have 0.5, 0.1, and 0.05, 0.1, and 0.2 molar sodium hydroxide here on your upper left. And you can see the PFAS removal over, so that C over C naught is going to be a total PFAS removal over the course of this experiment. And so you can see that the 0.1 molar sodium hydroxide did the best as far as the removal of PFAS. But then if you go to the upper right, you're seeing that the more sodium hydroxide, the faster the defluorination is. And the rationale behind this, I don't know if it's been totally, if iterations of occurrence have done to do it, but the hypothesis would be that the higher sodium hydroxide slows the absorption of those parent compounds to the photocatalyst. However, it does increase the defluorination of them once they are absorbed. So we're getting a higher defluorination, but we're getting less of the parent compound absorbed in that time frame. And then other things to note here, what you're seeing is on the bottom left is going to be nitrate and nitrite. So there's a very high level of nitrate in it, and that is being reduced to nitrite and then removed out of the solution. And then on the bottom right, you're getting absorbance, and that's just to look a little bit about the DOM, the dissolved organic matter, that is, as we're seeing, pretty chromophoric DOM, so it's affecting the attenuation of that light through the reactor. So once those are absorbed or removed, then you get a higher rate of PFAS removal and subsequent degradation. Slide 27. So here, kind of looking into that, the slide previously was 10x dilution, and this is looking at some lower dilutions. So these still bonds, we concentrate them down. You have the ion exchange regenerate, and then you have it distilled into a brine. And we really don't want to reconstitute it back out. So we don't want to dilute it, or we want to dilute it as little as possible to be able to still treat it, just because of, capital cost of equipment with volume, and also you spend time and money into distilling it. So, there comes a point where it's not effective at a practical scale to dilute it back out. So what we have here is trying 5x and 2x dilutions. So again, because of one, very high concentrations of PFAS and other constituents like salts, and that chromophoric dissolved organic matter, you have a slower removal rate. So the less you dilute it, the slower the treatment's going to be. However, keep in mind you are treating a higher mass of PFAS over this time. So when it is normalized, which I believe is on a later slide, we can take a look at the normalization of the PFAS treatment over time to see, what's the most effective. But what you're seeing here is a little over 90% removal of those parent PFAS in both of them, both 5x and 2x dilutions, and then you're getting about a little over 90% in the 5x dilution and a little over 60% in the 2x dilution. And then on the bottom there, you're getting similar trends of nitrate and nitrate as you saw in the 10x, just what's changing there is that average reactive contact time. So the more the constituents in it, the longer it takes for that same representative treatment to take place. Slide 28. And this is just, again, what we saw in the 10x dilution treatment. Just, again, you're seeing more absorbance because it's diluted less, but this is that chromophoric DOM. So you're seeing very high DOMs here, and then over time that's removed out. Next slide. Slide 29, thank you. So this is a slide, this is showing kind of snapshots of the treatment over time and what's happening to both the media and the solution, along with normalized PFAS removal data on the graph there. So, what this is on the upper left, you're seeing 3 kind of snapshots of this media, and at the beginning of treatment, if you kind of take, if you stop the treatment and you took the media, you're seeing that chromophoric DOM absorbed to the media, and that is hypothetically what is impacting the PFAS treatment. So you have slower PFAS treatment at the beginning as you're degrading that DOM, and then as you move through treatment, you see the whitening of the media as that photocatalytic technology is reacting, and then at the end you see, it's fairly white at the end, and you're seeing similar things happening with the solution. So if you take the still bottoms, and then over time you can see the DOM clearing up, and so there are some delays in the PFAS reactions So the PFAS kinetics are a little faster toward the end of the treatment after the organic matter has been removed from the system. So there are methods where you could, focus this destructive treatment more so on the PFAS. You could do some pre-treatment of the still bottoms and remove some of these other constituents that aren't our target constituents, and that would save energy for removing PFAS. So you could focus on PFAS degradation. Slide 30. So from doing the still bottoms, there was three main things that we thought would be impacting the PFAS performance, and that was nitrate, TOC, and turbidity. So kind of took a step back from this and went back to PFAS spiked deionized water solutions and looked at these individual constituents. Slide 31. So what you're seeing here is potassium nitrate. Again, this is just in PFAS spiked deionized water with just potassium nitrate with a few different concentrations of that. So, we're seeing a control there where the control is getting, 95+% removal. And this is a mixture of PFAS compounds in it. So similarly representative of what the still bottoms had as far as PFAS goes. And then you're seeing the defluorination on the right. So you can see the more nitrate we add, the slower that PFAS removal and subsequent degradation is. Slide 32. And again, similar for total organic carbon, this definitely has a much stronger impact than the nitrate. So the more and this is specifically a chromophoric organic carbon. So this is an organic carbon that has some kind of color to it. So that's impacting attenuation of the light, and that's going to impact your PFAS degradation over time. So you're seeing a huge impact on PFAS removal and very little defluorination with large concentrations of this chromophoric organic carbon. Slide 33. And then the last one's going to be turbidity. Turbidity does impact, again, this is going to be, similar. The more turbid your solution is, the less light that can attenuate through the reactor. The slower your reaction is going to be. Again, this can be solved with some form of pretreatment. However, it can also be, just a slower reaction. So it really depends on what's needed on site. If the plan is just to have one system that can, be placed on site and just treat these still bottoms, and the time doesn't really matter. It's low volume, highly concentrated, and if it just needs to be treated before, the next regeneration, you might not need pretreatment. Other areas, if you need to treat a higher volume, it's probably more cost effective to have different pretreatment technologies on site in a treatment train with the UV SGM. So it's site dependent. Slide 34. So these are some results on some AFFF concentrate. So this is legacy AFFF, I believe. Yeah. So the highest concentration there is going to be PFOS. So this is a legacy AFFF. So a PFOS dominant, not a fluorotelomere dominant AFFF. And what you see here is a very high concentrations of PFAS, but in a long reactive time. However, you're getting very good removal of PFOS and PFOA, which are some of the regulated constituents and what's predominantly consisting of this AFFF. And then you're seeing defluorination above 100. The reason for that is because the sum of PFAS over here on this table is just going to be the sum of target PFAS, and in an AFFF you're going to have, even though it is a legacy AFFF, you're still going to have some constituents that are non-target, definitely less than if you would have a fluorotelomere AFFF. And there also may be some concentration of the solution over time. These are small batch treatment experiments and taking large amounts of sample over time with some heat I mean, less than 40 degrees C, but some heat from the lamps heats up the water. So you get a little bit of evaporation of the solution. So you can have some concentration of the solution at these small scales. So that could also be some reasoning for that percent defluorination being above 100%. And then that's also going to impact what your PFAS percentage is going to be. And then on the bottom there, what you're seeing is fluorine NMR. And so you can see the untreated and treated. So the untreated, you see all the peaks for, the CF2, CF3s. And then in the treated one, you can't really see, there are some tiny peaks on that line. But since there's such a high concentration of fluoride, you're seeing a huge peak of inorganic fluoride. So that's just showing you the ratio of the concentration of inorganic fluoride to organic fluorine. And you can see that you're getting effective treatment of this AFFF, just another line of evidence aside from, the normal ion chromatography that we normally do to get defluorination. I'm now going to hand it over to Dr. Megan Hart, and she'll finish up this presentation.
In order to figure out how this is the most effective, we needed to determine how the breakdown mechanisms were occurring. So what we did is we wanted to figure out, was it the nucleophilic attack, was it the photocatalytic attack, or do we need both in order to figure out what is the effective mechanism? So we isolated each PFOA, PFOS, and 6-2 FTS, and we performed the experiments again, just to see with some scavengers, some radical scavengers, just to see which of the radical scavengers was decreasing our removal. And on the top right, you can see here's PFOA, and in PFOA, we use potassium iodide, some IPA, some benzoquinine, and DMSO in order to reduce the holes, the electrons, the hydroxyls, and the superoxides within the solutions that might be occurring and being responsible for the degradation. And what we see is that there are three main things that are responsible for PFOA. It's excited electrons, photoexcited holes, and hydroxyl radicals. And they seem to be the most responsible for the degradation. So these are the green, the purple, and the red line above that black line in the top right corner there. And yes, the blue line is there, and it is above the control. So it does play a role in the degradation of PFOA. It is not as responsible as the excited electrons. In PFOS, it's a little convoluted, the data down here, that the black line is in the middle. And as you can see, DMSO actually increases the rate of degradation of PFOS. The same thing occurs when we do the IPA. So those two should be knocking out our holes and our electrons. So what we see is that the holes and the electrons seem to be the most important thing for the PFOS, and the hydroxyl radicals are sort of important, but we're not quite sure to what extent. There's still a lot of work that needs to be done on this area because we're still not quite sure. There could be a combination of different things. So we have about 6 more experiments we'd like to run on this. We still get the same end products. We end up with aqueous fluoride, aqueous acetate, formate, sulfate, and nitrate. The nitrate reduces into nitrite, just like the PFOA and PFOS seem to be reducing. Other ongoing tests we have realized that this is a really robust and stable material. We can incorporate pretty much anything we want to into it. It just may take a little bit of manipulation. And what we found is that there are some metallic organic frameworks that seem to enhance performance. MIL 125 seems to also enhance performance. And then boron nitride also seems to enhance performance. So in the top right, we have our metallic organic framework, the MIL 125 that we're using. And as you can see, it doesn't seem to really enhance the PFOS degradation, but it really accelerates the PFBS degradation. And so the shorter chain degradation is where a lot of the photocatalytic medias or the photocatalytic technologies seem to struggle. That's because it has to absorb to the photocatalyst in order to be destroyed. This seems to enhance absorption, or at least bring it into contact with the destructive scavenger or the destructive radical that is there. Boron nitride also seems to enhance the rate at which PFAS degrades, and I'll show you that in the next slide. These are columns that we're going to use in our field deployable system. They're about 4.5 feet tall. They weigh about 85 pounds, and the light goes through the center of it. And just like the other ones, we packed the media around it, and then we started treating things with higher wattage lamps, just to see what the impact of the wattage of lamp has on the degradation. And I don't have the answers for that right now. That's still ongoing work, but we are looking at that. The co-contaminants can really degrade or delay the PFAS treatment. And so do we need pre-treatment before we go out in the field? And that's going to be waste dependent. And the waste dependent treatment could be a green sand in the front end, or I know some of the other UV technologies use a membrane to remove the color or some of the chromophores before it hits them, so they're able to stay in solution. The thing that makes us unique is that we don't really care about the salts. We stay deployable even if there's a lot of salts in there. Mainly, it doesn't salt out, and that makes us unique in the area of photocatalytic materials. The next steps, we are going to continue looking at and characterizing the response of the boron nitride and the metallic organic frameworks in series. So we want to see if we put our UV SGM in a series, followed by photolysis, followed by maybe a MOF-based SGM or a BN-based SGM. What happens then? Can we target the short chains in that last column? So there's the BN, or our boron nitride SGM there in the middle. And we went from the piped column reactors on the top right to these medium-sized reactors in the middle, to those large-sized reactors that you saw on the last slide. So if we look in the bottom right, we can see the PFAS destruction without the boron nitride. And the rate is actually pretty good for destruction. And this is from our original Willow Grove's work for just PFAS. When we add that to the boron nitride, we get an enhanced rate of reduction, and it's about 3 times accelerated, which makes the boron nitride an ideal candidate for focusing on some of the other longer chains or sulfonate-based PFAS. Things we want to know, using our current understanding of free radical scavenger, how to optimize the amendments. So the sodium hydroxides or the boron nitrides, the MOFs, how do we make this optimal for use in the field? And then how many times can we reuse it? We know it's self-cleaning. It's pretty stable, but how long will it stay stable? And then we wanted to know what the effect of various light modality and modularity are. The position as well as the strength of the light. So our goals in the next, in our ESTCP project, is to optimize our light configurations with hopefully a new design. This should reduce our time on the site. That will reduce our operation and maintenance costs and maximize our efficiency. We want to determine the actual life cycle of the system. Again, we haven't seen degradation of the material after treatment, but we haven't really challenged it with multiple different wastes repeatedly, mainly because we want to make sure we're actually treating the thing that we're treating at that point in time. So do they work multiple times for different wastes? Can I take it from a rinsate to a leachate and then off to a soil rinsate? How do I deal with alcohols? That's true for any photocatalytic material. Alcohols are not really good. They shut down our processes. So how do I combat them? And then I need to come up with a way to operate in a long-term stable managed position or a manner So we want to be able to demonstrate that this will be operational and mobile for quite a long time. All right. So on this left is our foam fractionate. And this is foam fractionate from a groundwater well. It's on the eastern coast from a former naval facility. And our degradation of the foam fractionate was hindered by the presence of alcohol. And we had to come up with some really creative ways for reducing the amount of alcohol in the solution, or at least combating the alcohol so that our free radicals could be formed. How we could fit in a foam fractionate system, we could fit within as a polishing sequence. So we would fit here in the middle of the system. It would come out, be collected, then treated by our system, and then held in a holding tank until we reached a certain amount of solution, which could then be discharged into the water. So we would be able to meet the criteria for groundwater. If we were in a still bottoms setup, we would work within the ion exchange influent. It would still be a brine when it comes back out. We can't destroy the salts. We don't actually remove the salts, but the salts don't hinder our ability to treat either. So the ion exchange would be regenerated on site. You distill it down, and either we would dilute it to make it not crystallize when you have all that salt in it, or to reduce some of the color, or maybe a pretreatment, I don't know. And then it would pass through our system to a holding tank. And then after talking with several of the vendors for ion exchange, they think that it would be fine to put back into the front of the system. UV-SGM is really a fairly easy to scale and deploy material. You put it in columns, you send it out, you put it on site, and you set it and forget it. It goes and treats until you get the right treatment that you want. It has been able to destroy ion exchange resin brines from still bottoms when others were not. We're able to treat AFFF concentrates, foam fractionates, and we've looked at some rinsates as well. We're easy to scale for our site demonstration, so hopefully look for some news about that in the near future. There are co-contaminants that may moderately affect in performance, but there are ways to work around that. And again, if you don't want to work around that, that's okay, because the media itself acts as a filter. The UV-SGM is, we're preparing for the field right now. We're creating our design, and we're getting ready to move, hopefully next spring, out onto site. And then we're looking at optimizing everything before we get out there. The benefits to the DoD is they get a destructive and modular PFAS treatment system. It would provide minimal operational maintenance, and we would get in their way very little. So it would just set up in the corner, and they would take up a very small footprint and treat the solutions while they were able to go about their business. We have validated this in multiple concentrated liquid matrices. It works well under most water chemistries, though it can be limited under high turbidity and nitrates. And again, as I said, it's super low maintenance. You put it out there, you set it, it recycles until it hits the right fluoride concentration you want, and then you're able to release the water. I would really like to thank my partners on this project. I would like to thank my former and my current students, especially Dr. McIntyre, Geosyntec consultants who have been there to help propel the technology into the market. Savron Solutions for helping to design the newest and greatest reactor vessel, the Navy BRAC program for their real solutions, Black & Veatch's Award for Excellence in Sustainability and Environmental Engineering, and then Kaufman Award for Foundation Award for Entrepreneur Commercialization, Innovation, and Transformative Technology. If you have any questions or you would like any more information, here are the two various SERDP and ESTCP supported projects that we have for this technology, ER 19-1403 and ER 23-8372. Thank you.
Thank you, Megan, and also Hannah. We only have time for a few questions, so let me start with one with you, Megan, from the Pennsylvania Department of Environmental Protection. Can you elaborate on how nitrate potentially competes with the PFAS in solution?
So they compete for sites, reactive sites. It's a reductive technology, and nitrate will reduce if it's in contact with the free radicals. In this case, it would be the electrons that are doing the reduction. So our media produces electrons in holes. If we can suppress the holes, then we can reduce the nitrate faster. And then after reducing that, then we can move on to treat the PFAS. I hope that answers the question.
Thank you. And can you also elaborate on how well the photocatalysis works as a mechanism in turbid water? So
the media itself filters out most of the turbidity, and then it treats the media. The turbidity can slow down the ability to treat PFAS, but once it's removed from the solution, then it's off to the races. So it's really just a delay in the destruction of the PFAS. So are you worried about time on site? If you're worried about time on site, then you can remove the turbidity up front. If you're not, then you can just set it and forget it and let it remove the things itself.
Great, thank you. And there's at least 3-4 questions that have come in about the timing and next steps for demonstrations. You alluded to that in your presentation and provided the links to the projects, but can you provide a short timeline to address these questions, Megan?
It looks like we'll be on site, I would say late spring, early summer, and the sites are still to be selected. It looks like it'll be somewhere on the East Coast and maybe someone out towards West. And I can't give the sites right now, but the timeline is it's coming fast. In other words, we're moving as fast as we can.
Great, thank you. This next question is from the Colorado School of Mines on your still bottom data with nitrate and nitrite. You showed an associated lag in PFAS degradation until the nitrite are consumed. That seems to point to hydrated electrons being the key reactive species. Do you also see the PFSA chain length dependence documented for hydrated electron technologies?
We see that the chain length is important for whether or not we need hydroxyls or the electrons present. I would agree with that statement. It does kind of hint towards that hydroxyls, but the hydroxyls are coming from another mechanism within the electrons and the superoxides reacting.
Thank you, Megan. And one last question. Can you summarize, this is from Trey Merigi, this question, can you summarize the advantage of using this novel photocatalytic remediation method? For example, is it reduced energy relative to thermally based methods?
We compare our EEO based upon the parent product of PFOS in a paper, a scalability and reproducibility paper. And we are lower or on par with some of the thermal technologies. It is lower in the fact that we don't have to do pretreatment, and that's because we didn't do pretreatment at that point in time. Now, if I'd done the pretreatment that some of the other ones had, I probably would be a much lower EEO.
Great. Thank you again, Megan, for jumping in despite being ill with COVID. And thank you, Hannah, for stepping up and helping with the first part of the presentation. There are additional questions that we're not going to have time to address, so we'll drop the email addresses for you to contact the speakers directly. But at this point, we are going to shift gears to our second presentation by Dr. Brian Pinkard. Brian is the CTO and co-founder of Aquaga, a clean technology startup based in Tacoma, Washington, which focuses on bringing emerging PFAS technologies to market. Brian has served as a co-PI on research projects funded by NSF, EPA, the Air Force, and the Defense Advanced Research Project agencies. He's also doing projects for SERDP, ESTCP, the FAA, and the NDCE. Brian's primary area of technical expertise is in the reaction kinetics and mechanisms of recalcitrant compounds reacting under hydrothermal conditions, and that includes both subcritical and supercritical water environments. For his work at Aquaga, Brian was included on the Forbes 30 Under 30 list in 2023 and was awarded first prize in US EPA's Innovative Ways to Destroy PFAS Challenge in 2021. He has an affiliate assistant professor appointment in the mechanical engineering department at the University of Washington, where he received both his master's and doctoral degrees. Brian, please go ahead with your presentation.
Thank you, Rula. It's good to be here today. I'm excited to be presenting on the hydrothermal alkaline treatment technology, or HALT. This is a technology that's come out of the SERDP ESTCP program from the start. And today I'll be talking about some of our efforts to scale up the technology for commercial applications for the DoD, some ongoing optimization efforts that we have funded through the ESTCP program, and some upcoming demonstration efforts. So first I'll be talking a little bit about HALT itself, how it works, what the technology is, presenting state of the science, our current understanding of how the technology works. I'll be talking about our ESTCP project ER21-7591, which is focused on optimizing the HALT technology. And then I'll also be talking about our ESTCP project ER23-8400, which is focused on demonstrating HALT at scale for some DoD relevant feedstocks. I'll close out by talking about future directions for the technologies, as well as benefits to the DoD, and then hopefully we'll still have some time for questions at the end. So to kick us off, HALT is a thermochemical process that takes place under so-called subcritical water conditions. So subcritical water is really water that's in a liquid phase at temperatures above 100 degrees Celsius, above the boiling temperature at atmospheric pressure. The way we stay in a liquid phase under these conditions is by staying at higher pressures. If you go to high enough temperatures and pressures, you enter a supercritical phase, which is kind of like a dense steam. So we very intentionally stay in this liquid phase that allows us to increase the pH through the addition of sodium hydroxide, which is how we drive these PFAS destruction reactions. And there are some real tangible benefits to operating in a liquid phase. We can keep salts soluble when we're processing real feedstocks. We can add sodium hydroxide, as mentioned. So we kind of operate at this range of 300 to 374 degrees Celsius, high pressures, high pH, above 14. And what we found is PFAS really just fall apart under these conditions. So HALT was first demonstrated under SERDP project ER18-1501. This was a SERDP project led by Dr. Tim Strathman at the Colorado School of Mines. And the first study, the first application of HALT really focused on destroying and defluorinating PFAS. And since then, Tim's group has demonstrated that HALT works to destroy PFAS in AFFF formulations. It works to destroy PFAS in groundwater, works to destroy PFAS in foam fractionate, works to destroy PFAS on spent GAC. And everything that we've seen so far indicates that HALT works to destroy all types of PFAS, from ultra short chains to long chains, as well as different types. So PFSAs, perfluorosulfonic acids, perfluorocarboxylic acids, fluorotelomere compounds. Seems to be very effective across all types of PFAS, This has been evaluated with a wide range of analytical techniques, and it seems to be fairly matrix independent. The technology works even if there's a lot of other stuff in the water. So again, the first study that was performed really focused on destroying and defluorinating PFOS. And what was found was that the rate of PFAS destruction was highly dependent on two factors: temperature and sodium hydroxide concentration. So what you can see in the plots here is if we go from 1 molar sodium hydroxide up to 5 molar sodium hydroxide, we see much more rapid PFOS destruction. And for all these conditions, we see a pretty close closure of the fluorine mass balance when we bring the reaction over to completion. So when we're approaching 100% PFOS degradation, we see roughly 100% defluorination. That's what we want to see. With all of these destructive processes, the goal is to convert the fluorine in the PFAS molecule over into inorganic fluoride. In our case, that's sodium fluoride, could be other types of fluorides. If we've done that, then we've done our job. We're not producing any other organofluorine compounds, which could be problematic. What we've found so far consistently across a number of studies is that these temperature dependencies, the sodium hydroxide dependencies, are most pronounced for the perfluorosulfonic acids. So compounds like PFOS, PFBS, PFHXS tend to be the most recalcitrant in HALT and tend to have the highest dependency on the sodium hydroxide dosing. Now, this is not the case for perfluorocarboxylic acids, PFCAs. So what we've found with the PFCAs and also a lot of the fluorotelmer compounds, these compounds will degrade thermally in water, and they'll degrade into hydrofluorocarbons in the absence of an alkaline amendment. So if you put a compound like, in this case, trifluoroacetic acid, which is the simplest PFCA, the ultra short chain PFAS. If you put TFA in water and you heat it up to 200 degrees Celsius, TFA will degrade and it will turn into a compound called fluoroform, which is CF3H. And that's what you're seeing in this FTIR data down here. Now, fluoroform is non-toxic. It's really a greenhouse gas, so it doesn't have the same toxicity and health impact concerns as PFAS, but it's not great to be forming. And we've seen this across the whole range of PFCAs. If you go up to PFOA, it's the same trend. We form these 1H perfluoroalkane compounds. Now, if you have sodium hydroxide present, or if you have any hydroxide present, you end up forming no gaseous products, no hydrofluorocarbons. So in this FTIR plot down here, this is from the same study with TFA. As soon as we add sodium hydroxide in this blue line, all of the fluoroform disappears. We don't see any of it coming out of the system. And we're able to close the fluorine mass balance. So if you have a PFCA, and you heat it up in the presence of an alkaline solution, it's quite easy to mineralize all those compounds through this intermediate hydrofluorocarbon compound into final products of fluoride, carbonate, formate, and that's what we've seen here. With the PFCAs, we're able to destroy them under fairly mild conditions. What I mean by that is lower temperatures, lower sodium hydroxide dosing. So in this case, 0.4 molar sodium hydroxide is sufficient to destroy TFA in a fairly short time scale, as opposed to the PFSAs. So to summarize, we know how to destroy perfluorocarboxylic acids under very mild conditions. That trend seems to hold for the fluorotelmer compounds. However, the PFSAs require a higher sodium hydroxide concentration, and in the previous study up to 5 molar sodium hydroxide. Mechanistically, we think that the PFSAs require a nucleophilic substitution mechanism. This is why you need the higher concentration of sodium hydroxide. Ultimately, we produce similar end products of fluoride, carbonate, and sulfate. But practically speaking, we have a lot of motivation to reduce sodium hydroxide consumption if we're treating PFSAs. And we commonly see compounds like PFOS in the feedstocks that we're treating. So it leads to the question, how can we reduce sodium hydroxide usage when treating PFSAs. So that leads us to some motivation behind Project ER21-7591. So what we looked at in lab scale reactors is, okay, this reaction we know is very temperature dependent and sodium hydroxide dependent. Can we tweak the temperature a little higher to reduce our sodium hydroxide usage? And that's what you're seeing on the right here. So we did some studies with trifluoromethyl acid in partnership with the University of Washington. And we tested operating at 350 degrees C, and we tested operating at 380 degrees C. What you can see is that just by bumping up the temperature by about 30 degrees Celsius for the same time scale and the same chemical loadings, we can almost double the destruction and defluorination efficiency. So 2 molar sodium hydroxide, we go from 50% destruction of TFMS up to over 90% destruction of TFMS just with the 30-degree temperature increase. So that begs the question, can we translate these conditions to a larger scale system? There's also a question, how do we operate above 380 degrees C when the critical temperature of water is 374 degrees C? I'll come back to that in just a second. So the goals of our ESTCP project here, number one, to reduce sodium hydroxide usage. Sodium hydroxide dosing and subsequent neutralization is the primary driver of our operating costs for HALT at scale. It also introduces a decent amount of operational complexity to doing HALT. You have to mix your sodium hydroxide into your feedstock. It's complicated to do by hand. It's complicated to do with automated equipment. We then have to neutralize the pH of our effluent. That's a chemical cost. It's also corrosive to system components. So if we can bring down the amount of sodium hydroxide that we're using, there are a lot of tangible practical benefits. At the same time, we still want to maximize our destruction and removal efficiency with our HALT systems. And another goal on this project is to demonstrate that we can operate HALT systems, scaled up HALT systems in a long-term stable manner. So we've done the work on this project in the system that's pictured here. We call this our pilot series HALT system. This will process about 1 gallon per hour of PFAS-rich liquids. So again, sodium hydroxide and temperature dramatically affect our destruction rate. So can we increase the temperature past the critical point of pure water and still remain in a liquid phase? The answer is yes, we can do that. And we do that by adding salts. So this is a similar phenomenon to if you add salt to ice, it impacts the freezing temperature, or if you add salt to water, it impacts the boiling temperature, like if you're cooking pasta. If we add salts into our liquids, it increases the critical temperature of that aqueous mixture. And when you're running HALT, you naturally have to add sodium hydroxide, that's a salt. There's also sodium chloride present in many feedstocks that we typically look at treating, like sorbent regeneration brines, ion exchange regeneration brines, etc. So by playing with this effect, we can increase our operating temperature past 374 degrees C, and we can realize a lot of these tangible benefits of operating at higher temperatures, which is what you're seeing here. So in this study, on this project, we've used PFBS as a surrogate PFAS compound or as a model PFAS compound. The reason we've done this, PFBS is a PFSA, so it's fairly recalcitrant. It's also common. It's on the EPA's list of 6 compounds in the new MCLs. It's also got low surface activity. It's fairly water soluble, and this makes our experiments easier to run. We don't have to worry as much about compounds sticking to different surfaces in our experimental apparatus. So we're using PFBS as a model PFAS compound. In this study so far, we've operated with 1 molar sodium hydroxide. The data here on the right shows temperatures adjusted up to 390 degrees Celsius. And what you can see, this is initial concentration over final concentration. By going from 350 up to 390, we're increasing our destruction percentage from 30% up to over 90%. So that's very significant. And again, we're keeping the chemical composition the same. So slight temperature increase, 40 degrees C. From an energy perspective, that's not that significant, but we're seeing very, very striking differences in our destruction percentage. And we're seeing good fluorine mass balance closure. So in this project, we used a combination of LC-MS and ion selective electrode measurements to look at destruction and defluorination. Saw strong mass balance closure, as you can see on the right. Fluoride is being produced while we're destroying PFBS. That's what we want to see, and the mass balance closure is in line with what we've seen in previous studies, very close to 100%. So next steps on this project, we're continuing to optimize the PFBS destruction in this reactor system. We've now operated up to 400 degrees C. We're also planning to vary the sodium hydroxide concentrations and the residence times in the system to see if we can target over 99% PFBS destruction. This past week, we completed a week-long stability test with our pilot scale system, destroying foam fractionate. We operated for over 100 hours. We operated overnight in an unmanned capacity using remote operations. So really validating that we can run these systems for a long period of time without encountering practical limitations. And then the final steps of this project are to assess sort of the state of the reactor vessel on this system in the lens or through the lens of corrosion and system longevity. And that brings me to the second ESTCP project that I'll discuss on the call today, which is project ER23-8400. This is a project in collaboration with ESTCP as well as the Defense Innovation Unit. And the goal is to demonstrate a scaled up HALT system for various PFAS-rich liquids. So the system that you see pictured here on the right, this is our STEED series HALT system. This is a fully integrated commercial scale HALT system at technology readiness level of 7. That means it's a technology that's been validated in real operating environments at scale with real feedstocks. The system will treat up to 10 gallons per hour of PFAS-rich liquids and draws about 0.9 kilowatt hours per gallon during operations. The goal of this project is to demonstrate HALT at a Clean Earth facility in Charlotte, North Carolina. We will be treating 3 different feedstocks that are being produced during groundwater treatment operations. And those feedstocks consist of foam fractionate, an ion exchange regeneration brine, and a cyclodextrin regeneration brine. So the goal of this project is really to validate a centralized disposal model for PFAS-rich waste. So the idea is, if you have these contaminated sites, you can do pump and treat operations, you can treat surface water, you can treat groundwater with these various PFAS separation and concentration technologies. All of these produce a small volume of liquid concentrate that needs destructive treatment. And in many cases, it will probably make sense to ship those concentrates to a centralized, permitted, private facility where we can operate a destructive technology for that final destruction and disposal. This might be more cost effective than, for example, shipping systems around, destruction systems around to different sites. But one of the goals of this project is to really validate, how cost effective is it to do this centralized disposal versus a decentralized approach. So far on this project, the Aquaga teams conducted a site visit, helped coordinate some pre-mobilization needs. We've supported some of the permitting on the project, and we're currently getting started with some bench testing to assess feedstock compatibility. So we want to make sure that any surfactants that are being used in the foam fractionation process are compatible with HALT, as well as any solvents being used in the sorbent regeneration process. And what we've actually seen so far is that some of those solvents may have a beneficial effect on the HALT process and help driving the PFAS destruction reactions. This is a snapshot of some HALT field demonstrations that have been done or are upcoming within the DoD context. So in May, we were down at Beale Air Force Base. where we process 300 gallons of foam fractionate and 100 gallons of AFFF concentrate over the course of a couple weeks. And in the next year, we'll be down at the North Carolina site, as mentioned, as well as a demonstration site at Peterson Space Force Base in Colorado under a project led by Dr. Chris Higgins. And then we'll be out at Travis Air Force Base under a project led by Dr. Chris Bologna. And lastly, as far as practical implementation of HALT, really similar to what Megan was mentioning with the UV process, HALT is a secondary or tertiary treatment process when we think about PFAS. So the goal is to couple this with separation and concentration technologies to facilitate the outcome that the client is looking for, where you take PFAS impacted water and you output nothing but treated water that can be discharged. So if we have, for example, a foam fractionation system treating this water, producing a PFAS-rich waste, our ideal scenario is we treat the PFAS-rich liquids with HALT, and then we output our effluent back into the headworks of the overall treatment train so that any potential residual PFAS can be captured and kept in this closed loop. This can be implemented for foam fractionation. This can also be implemented for regenerable sorbent technologies. The goal is to deliver the outcome that the client is looking for, which is treated water that can be discharged. So to conclude, HALT works to destroy all known classes of PFAS via several different reaction mechanisms, including thermal mechanisms, nucleophilic mechanisms. Current efforts funded by ESTCP are bringing down the cost and complexity of HALT processing through reducing our NaOH consumption, our sodium hydroxide consumption, and HALT is currently being demonstrated at scale, and commercial scale systems are currently available. The benefits to the DoD, HALT is ideal and effective for destroying all types of PFAS that reduces long-term liability associated with these wastes. HALT is currently capable of treating concentrated liquid matrices from real field operations, including foam fractionate, sorbent regeneration brines, AFFF, membrane concentrates. And overall, HALT enables a safe and responsible separation, concentration, and destruction of PFAS, which is the outcome that we're all working towards. So with that, I'm happy to open it up for questions, and Rula, I'll pass it back to you.
Thank you for go ahead.
Sorry, just real quick, I want to acknowledge collaborators, Gus and Conrad from our team, Colorado School of Mines team, Dr. Strathman, Dr. Higgins, Dr. Howell, Dr. Cronmiller, and Ori Soker, from University of Washington, Dr. Vasilov, and Malpure Heat, and Isabella Rios, and then to yourself, Rula, Dr. Rula Deeb, and Dr. Dave Major from Geosyntec. There's really been a team working to bring this technology to field. Sorry, Rula, I'll pass back to you. Thanks.
Oh, great. No, thank you so much, Brian. Outstanding presentation. We have a number of questions that we're going to ask over the next 11 minutes. We're going to start with one from the U.S. Coast Guard Office of Environmental Management. How much energy is required with the whole process, and what is the source of heat energy used?
Great question. So as mentioned, we're sort of in that 1 kilowatt hour per gallon range. One of the benefits of staying in a liquid phase is you never have to heat through a phase transition. That keeps our heating costs down. And that energy usage really holds for different system sizes, from our commercial scale systems down to the smaller systems. All of our heat is electrical heat. So we have no emissions on our systems. There's no there's no combustion processes taking place. We have 2 power hookups on that Steed series system. One's a 60 amp 480 volt connection, one's a 20 amp 480 volt connection, and that's all we need to power and heat the systems.
Thank you, Brian. This next question is from Lockheed Martin. Will the whole equipment be available for companies to purchase? And if so, when will this product be available?
Yes, so our business model is to manufacture systems and then offer them for sale or for lease. And we currently are taking orders for those Steed series systems, as well as manufacturing and building out a larger scale system and a smaller scale system that will be available in 2025. So we're ready. We've got a commercially ready system. We're taking orders.
Wonderful. And again, if you are interested in the contact information for all our speakers, you can download a copy of the PDF of the slides, and the contact info is posted there. The link is already in the chat if you want to scroll up. Otherwise, we can try and drop it again. All right. This next question is from Framergy. Does the HOLT mechanism generate hydrogen fluoride gas during destruction? And have you measured the output gas composition?
So one of the advantages of operating in an alkaline high pH environment is that we've never had to worry about hydrofluoric acid. So any fluorine that's converted over to fluoride ends up as dissolved fluoride, sodium fluoride. There's no HF produced. We have done gas sampling and characterization. Some of that's been done at the lab scale, as I presented from that trifluoroacetic acid study that was published earlier this year. And then on many of our demonstration projects, we are performing OTM 45, OTM 50, and OTM 55, which are all analytical methods to characterize aerosolized PFAS or volatile fluorocarbons. We're currently waiting on some OTM 50 results from one of our projects, but broadly, we haven't seen anything to be concerned about so far.
Thank you so much. This next question is from the Center for PFAS Solutions. What happens to the nitrates and nitrites during the whole process?
It comes along for the ride. So we've done some studies with ions, looking at ion levels before and after, and for chloride, for nitrate, for nitrite, for sulfate, those ion concentrations stay constant from the start to the finish. So there's really no active mechanisms involving those compounds at these conditions.
Thank you. This next question is all the way from India, from the Council of Scientific and Industrial Research at the National Institute for Interdisciplinary Science and Technology. What do you do with the concentrated sludge after treatment? Do you believe that disposal of the sludge will pose any challenges?
Yeah, so we really produce a brine after treatment. So the characteristics of our effluent really is it's an aqueous mixture. It's liquid. Typically contains high concentrations of sodium chloride that from the sodium hydroxide that's subsequently been neutralized, as well as some concentration of sodium fluoride, some sodium carbonate, some sodium sulfate. Depending on the starting PFAS concentrations, we might see sodium fluoride in the parts per billion levels. We might see it in the parts per million levels. The biggest challenge that we have is managing the really the conductivity and the salinity of the effluent. So we can manage that in a few different ways. In some scenarios, we'd probably end up sticking that material in a landfill. In some scenarios, we can dilute that, again, kind of by passing that liquid back through the entire treatment train to meet any sort of local wastewater treatment plant permit requirements. It really depends on the location. Again, it's mostly a brine management problem.
Thank you, Brian. We've got several questions about practical applications for HALT and where they're best suited for use. One of them is from the Pennsylvania Department of Environmental Protection. Mm-hmm. So the understanding is that HALT will allow for PFAS destruction on site from brine sludges collected from on-site water PFAS treatment can you elaborate if this is what you're saying and maybe broaden your discussion to address other questions that are coming in into the most promising and practical applications for HALT?
Great question. Yeah. Practical applications for PFAS destruction. We really want to treat highly concentrated PFAS-rich liquids. Those are the best applications. So a perfect example of that is AFFF, bulk AFFF. It's very concentrated with PFAS. It's in a liquid phase. But a lot of facilities that have AFFF might only have 10 gallons or 20 gallons in a couple of totes. So it doesn't necessarily make sense to bring a whole, PFAS destruction system to a site just to treat 20 gallons. In that scenario, it probably makes sense to collect that material, send it to a permitted treatment, storage, and disposal facility where a HALT system can be located to process those wastes. Beyond the obvious, treating bulk AFFF, we think about, where does it logically make the most sense to implement treatment? One case is the industrial wastewater discharge of facilities that either manufacture or use PFAS in their manufacturing processes. Those tend to have PFAS, very high PFAS concentrations. Landfill leachate treatment is a logical location for PFAS treatment because so many materials are already being collected in the landfill. And then that effluent liquid is typically going to a wastewater treatment plant, as well as treating liquids on sites. So at DoD facilities, that might be fire training ponds, that might be holding tanks, that might be foam suppression systems and aircraft hangars. It might be treating groundwater directly. And depending on, again, the volume that's being treated, the PFAS concentrations of that treatment, it may or may not make sense to have the HALT system at the site alongside the concentration technology, or it might make sense to have the HALT system in a centralized location where you can ship the concentrates periodically as you generate them. One other thing I was going to mention. Oh, another thing that we're seeing is, wastewater treatment plants are thinking a lot about PFAS right now. We have a demonstration project coming up here in Tacoma at the wastewater treatment plant where we'll be treating sort of a side stream. But what we're seeing is that a lot of wastewater treatment plants are starting to implement industrial pretreatment programs with dischargers to the wastewater treatment plant and really pushing to treat PFAS at the source of where the PFAS is being discharged from. So that again goes back to the industrial facilities, the landfills, etc. So hopefully that answered the question at some level.
It does, and just 3 related questions. You answered whether HALT can treat AFFF, but for the AFFF concentrate and for the landfill leachates, do you need any pre-treatment or you're good to go? You just put it in the machine?
Yeah, it's a great question. Sort of the biggest challenges that we have are just some practical water treatment challenges. So with landfill leachate, we might have to manage some calcium and magnesium in our systems. We can either do that with some water softening upstream, or we can do that through some periodic kind of clean in place procedures. And then as far as AFFF, we do have to do a little bit of dilution of that material and manage some of the I guess practical challenges of handling that feedstock. There's some complexities with the glycols and with some of the other surfactants that are in there. So that's actually some ongoing work that we have that's funded through the NDCE program to keep figuring some of those practical challenges out. But broadly speaking, we saw really great results from that demonstration that we did back in May. Looking forward to getting a complete package of results that we can present out to the community.
Great. And one last quick question. How do you manage, this is from Clean Waters LLC, how do you manage and dispose of sodium fluoride as a byproduct given its CERCLA has substance designation?
Yeah, again, that's a concentration question, really. I mean, there's sodium fluoride in our drinking water at 700 parts per billion. So it really depends on how much is in the waste. And then once we perform that dilution, as we discharge things, how much is in there, if that's a problem for the wastewater treatment plant. So that's one issue that in some scenarios can be managed just through dilution. We have very high concentrations, like if we're processing AFFF and producing, a lot of sodium fluoride. There's some standard techniques to manage fluoride in brines, like calcium addition and precipitation.
Wonderful. Well, thank you again, Brian. You did a fantastic job with your presentation as usual, and the Q&A was really engaging. We're going to go ahead and wrap up, but remind you that our next webinar is in 2 weeks on DoD-funded research efforts to understand the effects of multiple stressors on marine mammals and terrestrial species. Registration is open for this webinar and for webinars to the end of the year, so please visit the SERDP and ESTCP webinar webpage for registration information. And before we let you go, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you can take a quick moment to complete a survey that will pop up on your screen at this time. This concludes today's webcast. Thank you for joining us.